So I start again. Hello, my name is Finn. I'm going to present how to embed functional logic programming in Haskell by means of a compiler plugin. This is joint work with my colleague Kai, who's also sitting here, and Jan, who's not here, unfortunately. I will skip, or mostly skip, talking about functional logic programming, as we heard a bit of that. And especially I'm going to reduce this functional logic part to barely the minimum, which is in our case this nondeterministic choice operator. So basically we have a something that looks like a Haskell function here, and we've already heard that if we see this as curry code, and basically it would be valid curry code, it is basically like Haskell, but has a totally different semantic. So what we have here is we have an insert function that takes an element and a list, and which this function should do is to non-deterministically insert the element x into the second argument. And this is done by either introducing the x into the empty list by returning a singleton list, or if we have a non-empty list, we can either insert the element at the front or do that by non-deterministically inserting it in the rest, or in the tail of the list. And the power of function logic programming now is that we can integrate this with normal functions. So for example, we can write something like this, a permutations function, which should take a list and return, well, all permutations of that list. We can use the non-deterministic insert function we have here for generating all permutations of a list by inserting the x in every position of the permutations of the tail of the input list. Most notably here is that, and we've seen this in curry, we have the effect of the non-deterministic non-determinism implicit. So we have nothing which indicates that we have non-determinism in the type or something like that. And well, while this is a neat-looking program, and it looks like a Haskell program, we cannot write this in Haskell, and we aim for being able to write something like this in Haskell. So what can you do in Haskell? Like, well, most of the times monads are very good thing. So the usual approach, or one approach you can achieve this in Haskell is by using a monad, which encapsulate this functional logic effect. Like I said, we concentrate on the non-determinism here, but there would be absolutely no reason why we wouldn't be able to support free variables and unification and everything we have seen in the talk before. And of course, if we have such a monad, we have to write some code in a monadic kind of way, and most of the time this code is not very, well, very pretty, and it's complicated. So, well, how could we do this? This is like a basic overview how we can transform this program in some kind of monadic program. And well, first step maybe you think of is, okay, we need some kind of non-determinism in the result of our function. So we introduce this functional logic monad. I won't go into detail which or how this monad is implemented. There are several implementations available. Basically, all you have to think of, we have a monad that is capable of representing non-determinism and perhaps free variables and so on. And we use this monad in our implementation, which is now called FL for functional logic. So we can add the functional logic monad in the result of our functions. And of course, we then have to adjust our implementations to return some kind of monadic result. We can do so by introducing returns at these positions. And of course, we are still missing the second parts here concerning the function applications. And well, as our insert function now returns some monadic value, we cannot simply return that or use that value in our construction of the result list. So we have to basically bind the result of our recursive insert call and pack it again into a monadic result, which is done at the right part with a return. And something similar can be done for permutations, where we bind the result of the recursive permutations call and then use that result in the call to insert. So this would be one possibility to monadically transform our program we've seen in the beginning. And this would be, with the adequate monad, valid Haskell code. But this is not what we want. We aim for some, a seamless integration of functional logic programming in Haskell. And when I refer to the talk of Stephen beforehand, this especially means that we want to have laziness and everything we know from Haskell also in our functional logic embedding. So this kind of embedding is too strict because we always, if you consider this generation of permutations, we always have to generate all permutations because of this bind operator before we are even able to return a single result. So if we are only interested in, for example, one permutation, we still have to generate all of them, and it's generally not very efficient. And of course, we want to be efficient. So what can we do? We can build on this approach. I just will briefly summarize what can be done. And first of all, one step would be we also want our arguments of the function to accept monadic arguments in this case. So that the, in this case, non-determinism effect must not be evaluated if not needed. Unfortunately, that's not enough. First of all, we see that we cannot we cannot anymore pattern match on the second argument because now it's packed into our monad. So first have to unpack it, which can be again done by the bind operator here. And yeah, the same can be done for permutations, same issue here. But now we maybe think of, okay, we have non-strictness in the argument, but that's still not the whole story. We also want to be non-strict or be able to be non-strict in the components of our data types. So if you consider a list, we have a first element and a tail list. And in order to be able to also be non-strict in these data types, we have to introduce a new data type as a replacement for lists, which still has an empty list constructor. And the most notably thing here is that we also have now monadic components for our data type. So each component of constructors can now also have this function logic effect inside. And of course, then we have to adjust our pattern matching and the type of our insert function and also the permutations function. So we now pattern match on these new constructors. And well, the rest now is very technically, but basically we can adjust the right-hand sides of our cases now accordingly and end up with something like this, where we, similar to before, we just return a singleton list here in this case, or we replaced here the choice operator with a alternative operator or monad plus operator, which we require our function logic monad to implement, of course, to be an instance of monad plus to support non-determinism. And yeah, the permutations function looks quite the same nearly. It's perfectly fine. This code actually works. However, it's not the whole story. To be exact concerning the semantics, the call by need semantics of Haskell and the call by need semantics, which we want for our function logic embedding, there's still a couple of things missing. For example, we would require this function arrow also to be some kind of transformed with respect to the function logic monad. And most notably, we heard about this fundamental problem in function logic programming regarding call time choice and runtime choice. So far, this would only implement runtime choice, which most of the cases is not very intuitive. And in order to be able to support call time choice, there is still some work to be done, which we actually have done, but I'm not going to present this now in this talk. So yeah, basically this, you can imagine this is the final result of our monadic transformation. So maybe you can get an idea why we don't want to program this in Haskell and instead write, which we've seen at the beginning of the talk, which is basically curry code and looks much neater than this monadic code. So Still, the question remains, if we embedded some kind of this in Haskell, how can we interface this with Haskell? And well, basically, we provide such val functions. In this case, it's a val1 for some kind of unary function. You can, of course, generalize this kind of functions using, for example, template Haskell or something like that. And we remember that permutations was now, in this transformed setting, a function that takes some kind of monadic argument and returns some kind of monadic result. But in the Haskell world, we, of course, want to encapsulate this non-determinism in some way and also want to be able to input usual Haskell values or give Haskell values as an input for our permutations function. So what this eval function in this particular case does, it has the type that it takes some kind of unary function. In our case, it's the instantiation of the permutations functions with a list of int type, and takes a Haskell list of ints and returns a list of lists in this case to encapsulate the non-determinism. So the actual result of this call would be all permutations of the lists 1, 2, 3. Hopefully I did not forget any. But yeah, this would be an example how to use this in Haskell later on. So what is the idea of our work? Basically, we don't want to transform, well, we have to have some kind of monadic code in order to implement this effect in Haskell, but we don't want to do this by hand. So how do we can transform some kind of module which uses our embedding into a monadic module, which basically reprises the code you have seen before. And we do so by using a GHC plugin. That is kind of the contribution. What are the benefits of this approach? Well, first of all, we don't have to re-implement parts of a compiler like a parser, no type checking because we can rely on the type checking of the GHC. We have seen that the function logic embedding is basically Haskell, and since the function logic effect is implicit, the type system basically remains unchanged. So we can exactly use the typing as it is for Haskell programs. Yeah, second of all, the type information is present within the compiler, and we need it for our monadic transformation. So that's a big plus. We don't have to do type inference ourselves. And last but not least, it's pretty nice for the user of our embedding because we get good quality error messages. Well, at least if you consider GHC's error messages to be good, but if you do so, then we get exactly the same error messages, which are most of the time very helpful. So what does it mean for our example? We can actually write this program as it is, which looks, well, totally normal, and it's readable, it's composable. We can hopefully can all imagine to program in such a way. All we do is add some comment line at the beginning of a module, which basically says that the GHC should compile this module with our plugin. And what then happens in the background is this module gets transformed like we've seen before. And you have to do absolutely nothing other than adding the line at the beginning. So how does this plugin work? To be honest, it's not only one plugin, it's like a composition of 3 sub-plugins. We see here that we have the monadic transformation that implements basically what you've seen before. So that's just the transformation of some embedded module into the monadic module. And as you can see, it takes place after the type checker in this somehow shortened pipeline of the compiler. Well, why is that good? First of all, like I said, we have the type information present after the type checking, as type information has been have been added to the AST, and this is very good for our error messages. I mentioned already that type checking works just the same, and if we have a well, very simple module which does not use functional logic programming at all now. But if we consider this module to be compiled with our plugin, and you may notice that we call double here on a Boolean value, although double is defined on integer values, which obviously is a type error, and we get the type error we would also get for the Haskell program. So no additional effort is needed for any good type error messages. We get where the type error occurs. We have IDE support in this case. So basically you can use any IDE and get the highlight where the error occurred. You can fix it just the usual way. So what about the other orange rectangles here? We have this import check plugin. It's very simple. Why do we need that? Consider a module A where we have defined the double function, and a second module where we have the test expression from before. And this module B imports module A. In order to be working, we need double to be able to work with non-deterministic values. And in order to be able to work with non-deterministic values, we need double to be transformed. And we can ensure this by only allowing plugin compiled modules like module B to import other plugin compiled modules, which in this case would be A. So it's like a design choice to ensure that you can easily combine multiple functional logic modules with the embedded language of ours. So what about the, yeah?
Does that mean the standard value has to be filed?
Good question. Yeah, yeah. We provide a replacement for the standard prelude, but it's not much work. So basically, you can just recompile most of the stuff as it is, and we of course add this choice operator to it so that you can create this non-deterministic effect for yourself. Yeah. So what about the other rectangle here, the import constraint solver? It's a little bit more complicated, and there are more details on that in the paper. But basically, we can use the same example as before. So we have a module A where the double function is, and we have a module B where this double function is called. So what's the problem here now? If we consider our pipeline, we of course have a dependency between modules, and since module B depends on module A, we have to first compile module A. That's how the GHC works. So module A gets transformed first. If we take a look at the transformed module A, we see that the change of type here in the function double. Double now takes a monadic value instead of an int value, but we have seen that if we type check module B, that gets type checked just as usual as normal Haskell code. And for the Haskell code in module B, double now has the type flint to flint, and that's clearly not what we want in that case. So, well, briefly speaking, this import constraint solver, you can see that this part of the plugin attaches to the constraint solver, which in turn is attached to the type checker. So we can influence type checking in via our import constraint solver plugin. And basically what this plugin does is it tells GHC, hey, type check this with the following type, because we know it's a function from the transformed module, and after that everything works as expected and totally fine. So what this constraint solver plugin does, it ensures that type checking works for functions which come from imported modules that have been compiled with our plugin. Yeah, so what about other advantages? We see a bunch of language extensions here. Should be 19 actually. So one of the benefits is we can reuse many language extensions. In fact, 19 of the 30 most used extensions are supported by our plugin without much additional effort, if at all. So basically, we can use many language extensions in our embedding of functional logic programming. In contrast to Curry, for example, where much effort has been done for implementing several of these extensions, like, for example, type classes or multi-parameter type classes. And some of these extensions are really neat to use and often important to write concise and good readable programs. As an example, you don't have to understand this fully, but it's basically the same program you've seen before. We have an insert function and a permutations function, but we have a type class, to be honest, a multi-parameter type class here with functional dependencies. We also use view patterns here. So just to give an example that we actually can use these language extensions to use these extensions in our functional logic embedding. And this totally works fine. We can transform this code just as you see it here. And basically we get these language extensions for free. So last topic, what about embedding of other languages? You might thought of that this approach is basically independent from the actual monad we use. So this monadic transformation is independent of the functional logic monad. The only thing specific to functional logic programming here is the actual monad we use and the choice operator we need for introducing this effect. So you basically can say if you take another monad, you get another embedded language. And in fact, that's the case. So you can expect some, maybe Kai next year here to present another embedding of another language here. No, just kidding. We already have implemented some toy examples. For example, we thought of probabilistic programming. We have a strict functional language tested. You can change evaluation strategies. That's a bit more technical. But you can embed it without much effort just by changing the monad other languages. However, there are some limitations. One of them is we are restricted to the syntax of Haskell. It would be nice that, Curry or functional logic programming is a good example because the syntax is basically identical to Haskell. But if you think of other languages, you might want to add other syntax. Fortunately, there's a solution for that, or at least at the horizon. Kai has made a proposal. It's, I think, already ready to be merged for a plug-in swappable parser for the GHC. So we would be able to add additional syntax or even change the syntax completely. So you can think of our plugin overview to have another rectangle, so another plugin extension point we could use to give an even better embedding of other languages. And another point, so far, only standard monads are supported. So, for example, if we need some kind of index or graded monad to represent some kind of effect, this would be currently not possible. So to conclude or advertise our paper, what can you find in our paper? You find somehow the bullet points are missing. I don't know why, but you can find the monadic transformation in more detail on the paper, including the sharing problem, it's not actually a problem, but it's discussed there. We go in more detail about the import constraint solver. We talk about interfacing with Haskell, how you get rid of the nondeterministic effect, and basically how to encapsulate the results in a list. We discussed some alternative approaches. We decided to piggyback on the GHC in this case, but of course you can do other things as well. And we did discuss related work. And last but not least, there is a prototype available at GitHub where you can try this out for yourself. So thanks for your attention, and I'm open for questions.
Thank you, Finn. Questions?
Not being able to import regular Haskell modules in your modules seems rather harsh. So I would have expected if you did that, you would just automatically fmap any functions over the non-deterministic.
Yeah, that is a big problem. It's not easy to get the interaction right. Once you are in the non-deterministic world, you cannot use the Haskell function without problem concerning laziness or non-strictness. You can work around this. It's also possible to bypass this restriction by programming some functions yourself, or the way to go would be to recompile the standard library with our plugin.
How annoying.
We work on that, yeah.
Okay, I have so many questions, but possibly later.
I'm still available later and as well.
But kind of bouncing off that question, how feasible would it be to do kind of like the C++ template approach of anytime you encounter a function that you haven't already compiled, could you like compile that function on the fly for your non-determinism monad?
Yeah, do you want to say something about that? Or well, basically it's a design choice. You can do it function by function. That would be a little bit more complicated to implement, but this would be an alternative way to go. We also thought of like analyzing the demand on the function so that we can cope with the laziness when we encounter it, but haven't found well, all working solution that works for every cases yet.
Well, sorry, what I mean by that is anytime you encounter like a standard Haskell function that the user has called inside your code that you haven't already compiled.
Yeah, you could of course like do something like reflection, get the implementation of the function, get all functions involved with it would be possible in theory, but it's not as easy to implement, and the compiler not always has, I think, all information, but maybe we can take that discussion later. But sure, it's one point we thought of.
Thank you. I'm understanding you saying that your approach is basically, you said independent to the monad, so you can take any particular monad and use that for a new language extension. So
basically, yes.
Basically. So with some new convenient syntax. So then someone's going to say, well, I want to have state back in Haskell as if it were actually there, as opposed to being forced to use a state monad.
You can actually do that. For example, you can also get rid of the I/O monad, but it would be possible, totally. I think there are no more questions. Oh.
I'll do one last question. How is performance of this? Do you? I remember Stephen was saying that.
Yeah, good question. Yeah, actually, the best answer to that would be it depends, and it depends on the monad. So if you actually we have another paper where we implement curry as a monad, and with respect to as much efficiency as possible. And using that monad for the FL monad, we actually get a quite competitive performance. There's still room for improvements, but the performance depends on the monad you use, and of course, like you can be more efficient regarding sharing, or you can emulate sharing. There are many different ways to implement all this, but depending on your implementation, you can be quite efficient. And our curry monad, for example, is well one of the instances where we we are quite happy with the performance, I would say. So maybe we can benchmark against Stephen's implementation.
And if you had bracket macros, you wouldn't have to do any of this, right?
That's true. I think that's one of the points we discussed in related work, the relationship to bracket macros.
We need to talk to the Haskell guys.
All right. Thank you, Finn.
Thanks.